This presentation will run through chair conformations and their relative population at equilibrium. I will also discuss geometric and optical isomers. The two molecules that I will be focusing on to explain these topics should be on the next slide. The systematic name for the molecule drawn on the left is 4-phenyl cyclohexene carbonitrile. This is because the nitrile group attached to the cyclohexene is a suffix, i.e. carbonitrile, and the benzene ring attached to the fourth position or the fourth carbon on the cyclohexene ring is the prefix, i.e. phenyl group. Therefore, the systematic name is 4-phenyl cyclohexane carbonitrile. The molecule drawn on the right shows a cyclohexene ring with a fluorine on the first carbon and a methyl group on the second carbon. So the systematic name would be 1-fluoro-2-methyl cyclohexane. Cyclohexane can adopt two chair conformations, and in each, substituents can either be in axial positions, which is either up or down along the ring's axis, or equatorial positions, which is tilted outwards. In 4-phenyl cyclohexane carbonitrile, the cyclohexene ring has two substituents, a phenyl group on the fourth position and a nitrile group on the first. The two chair conformations that I've drawn are cis and trans 4-phenyl cyclohexane carbonitrile. In cis isomer, the phenyl group is in the equatorial position on the fourth carbon, and the nitrile group is in the axial position on the first carbon. And then over here, the positions are switched. In the trans isomer, both groups are in the equatorial positions on carbons 1 and 4. And then both positions change to axial, but they remain on carbon 1 and 4. In cyclohexane chair conformations, equatorial positions are generally preferred for larger groups, such as a phenyl group. This is because they minimize diaxial interactions. With this in mind, when cis 4-phenyl cyclohexane carbonitrile is at equilibrium, the effects of the substituents on cyclohexane cancel out, as one group must always be axial and one equatorial. However, the phenyl group has a higher preference for the equatorial position compared to the nitrile group. Therefore, the equatorial conformer over here is favoured. It will be more stable and more populated at the equilibrium. For trans 4-phenyl cyclohexane carbonitrile, the effects of the substituents add up, and the di-equatorial conformer dominates. In 1-fluoro-2-methyl cyclohexane, the cyclohexane ring again has two substituents, a fluorine on the first carbon and a methyl group on the second. I have drawn another two chair conformations of this molecule. In the cis 1-fluoro-2-methyl cyclohexane, the fluorine is in the axial position on the first carbon, and the methyl group is in the equatorial position on the second carbon. And again, these positions are switched. In the trans isomer, both substituents are in equatorial positions, and then over here, they both switch to axial positions. Now considering these chair conformations in equilibrium. In cis 1-fluoro-2-methyl cyclohexane, the effects of the substituents cancel out, as one group must always be equatorial and one axial. However, the methyl group has a greater preference for the equatorial position compared to the fluorine, so the equatorial conformer is favoured at equilibrium. On the other hand, in the trans isomer, the effects of the substituents add up, and once again the di-equatorial conformer dominates. Geometric isomers, also known as cis-trans isomers or EZ isomers, are a type of stereoisomer, where molecules have the same molecular formula and connectivity of atoms, but they differ in spatial arrangement of groups around a rigid structure, such as a double bond or a ring. This restricts rotation. Cis isomers are when two substituent groups are on the same side of a double bond or ring, as shown here. However, trans isomers are when the groups are on the opposite sides, just like here. Likewise, with EZ isomerism, the E isomer has the highest priority groups on the same side of the double bond, whereas the Z isomer has the groups on the opposite sides. To the left, I drew a structural isomer of 4-phenyl cyclohexane carbonitrile. I also identified the cis transisomers of the structural isomer. The systematic name is 2-phenyl cyclohexane carbonitrile. On this slide, I drew another structural isomer by changing the position of the phenyl group to the third position. Thus, the systematic name is 3-phenyl cyclohexane carbonitrile. Considering the molecule on the left, both groups, the phenyl and the nitrile, are on the same side of the ring. This makes it the cis isomer, whereas the skeletal structure on the right shows the groups are on the opposite sides of the ring, hence the trans isomer. Optical isomerism is where molecules have the same molecular formula, but they differ in spatial arrangement of atoms around one or more chiral carbons or chiral centers. This is a carbon atom attached to 4 different groups. This leads to non-superimposable mirror images called enantiomers. These enantiomers are distinct from each other in a way that they cannot be aligned perfectly when overlaid. This is similar to how our left and right hands are mirror images, but they are not identical. Here are little models where I've tried to show that enantiomers are non-superimposable mirror images. To the right, I've drawn a structural isomer of 1-fluoro-2-methyl cyclohexane. The systematic name for this structural isomer is 1-fluoro-2-methyl 3-ethyl cyclobutane, and this would be a good example of optical isomerism, as I've drawn here. The second carbon is bonded to 4 different groups: a hydrogen, a methyl group, an ethyl group, and then the rest of the cyclobutane ring, which is substituted with a fluorine atom at carbon 1. Due to being attached to 4 different groups, it is a chiral center. This allows the existence of 2 enantiomers, which are mirror images of each other. And there's the mirror plane in the middle. These 2 enantiomers would have identical properties except for the way they interact with plane polarized light. One enantiomer would rotate light clockwise and the other counterclockwise. A quick summary. We talked about systematic naming, chair conformation and their relative population at equilibrium. We also talked about geometric isomers and identified the cis and trans isomers. And then finally, we talked about optical isomers and how we differentiate between the 2 enantiomers. Thank you for watching.